All right, let's dive right into the absolute core conflict at the heart of structural engineering. In today's explainer, we're demystifying the limit state method, and we're going to look at the incredibly delicate, high-stakes balancing act that engineers have to perform every single day. Seriously, it's this eternal battle between preventing a catastrophic failure and just ensuring everyday usability. Think about this for a second. Would you buy a car that you know survives a massive crash, but it rattles like a literal tin can every single time you drive it down to the grocery store? Well, of course not. But conversely, a car with a perfectly smooth ride that crumples at the absolute slightest impact, that is a total death trap. Professor Arvind Deshmukh uses this brilliant analogy, and it perfectly captures exactly why structural engineers rely on the limit state method. They have to evaluate both the extreme safety and the daily comfort for pre-stressed concrete structures. You really can't have one without the other. So here is our roadmap for this explainer. We'll start with the two pillars of design, break down strength as the ultimate limit, and then look at serviceability for daily performance. After that, we'll crunch the actual numbers, see what happens when good designs fail, and wrap it all up with the soul of engineering.
Part 1, the two pillars of design, safety versus comfort.
Okay, so according to structural codes like IS 1343-2012, we basically have to split our design checks into two massive categories. This ensures a structure doesn't fail on either end of the extreme spectrum. On one side, you've got the ultimate limit state, which is all about pure strength. This is the stuff that prevents a total collapse during extreme, super rare events. Think major earthquakes, cyclones, or massive floods. But on the other side is the serviceability limit state, which is hyper-focused on daily performance. This is what ensures daily comfort and prevents that slow-moving long-term damage, like floors sagging or steel rusting under normal everyday loads, like regular foot traffic and heavy furniture. Moving right along to part 2, strength, the ultimate limit, preparing for the worst. Think of this strength pillar as the ultimate crash test rating for our pre-stressed concrete structures. When we talk about the ultimate limit state, we are literally defining the exact failure points we are desperately trying to avoid. We check flexural strength to prevent the beam from bending so much that it snaps. We check shear strength to avoid that terrifying diagonal cracking right near the supports. And of course, we check overall stability to ensure the whole structure doesn't just overturn or slide right away. A really fascinating detail here is that the pre-stressing process actually helps shear resistance, mostly because the compressive force it introduces delays that dangerous diagonal cracking. Now check out that massive 1.5 right there. When we're designing for the ultimate limit state, we don't just use the expected everyday weight of the building. No way. We magnify our characteristic dead and live loads by a factor of 1.5. This guarantees a massive safety buffer for those extreme, totally unpredictable events. We are mathematically preparing for the absolute worst-case scenario. All right, part 3, serviceability, daily performance, or as I kind of like to call it, the smooth ride. Stepping away from the disaster scenarios for a minute, this is actually where junior engineers tend to make their biggest mistakes. Serviceability limits aren't about collapse. They're really about aging gracefully. We've got stress limits, basically the no-crack rule, where we aim for zero tension in a fully pre-stressed member just to prevent premature crushing or cracking. We have deflection limits, the sag rule, so a bridge doesn't literally feel like a trampoline under your feet. And we have crack width limits, the rust rule, because even tiny microcracks can let salt water in, slowly corroding the steel over time. Notice that for these checks, we use a standard load factor of exactly 1.0. We aren't magnifying the loads here because we are evaluating normal, realistic, everyday conditions. Part 4, crunching the numbers and putting all this theory to the test. Because we're engineers, we have to prove our concepts with actual math, right? So here are the exact starting variables for a simply supported 8-meter spanned post-tension beam. It's 250 by 500 millimeters, and it's taking a live load of 12 kilonewtons per meter. Let's put the section through a super rigorous, dual-pillar mathematical check to see if it actually survives both everyday use and extreme stress. Let's walk through how this builds sequentially. Steps 1 and 2 validate that our mid-span stresses stay safely in compression under service loads, and they do, meaning it completely passes the daily stress test. Step 3 checks our short-term deflection. At a calculated 7.76 millimeters, it is well under the strict 32 millimeter limit, meaning no trampoline effect here. And finally, step 4 throws that big 1.5 ultimate load factor at it. the factored moment comes out to 181.5, which is safely below the beam's total capacity of 280. So this structure, it's perfectly safe and highly functional.
Part 5, when good designs fail, looking specifically at the danger of the smaller beam.
But what if we mess with the parameters? Say we try to use a smaller 200 by 400 millimeter beam, just to save a few bucks on materials. As we run the numbers on this smaller section, we discover a really terrifying hidden danger. If you look at the math for the everyday loads, the top and bottom stresses remain perfectly safe in compression. It passes the daily comfort test with flying colors. But the second we apply that 1.5 load factor for the ultimate limit state, the factored moment jumps to 168 kilonewton meters, completely surpassing its hypothetical capacity of 160. It entirely fails the ultimate strength test. It's a perfectly smooth ride right up until the exact moment it catastrophically collapses. Just to keep all of this perfectly organized for you, here is the synthesized checklist based on the structural codes that literally every single engineer has to follow. You can see the clear divide here. Serviceability is on the top using a 1.0 load factor to check stress and deflection, and ultimate is on the bottom using that 1.5 load factor to check for moment and shear failure. This checklist guarantees a structure is both completely safe in a disaster and perfectly functional for decades of normal use. And finally, Part 6, the soul of engineering and protecting future generations. Beyond all the strict checklists and the intense bending moments, we really must remember the profound professional weight of this discipline. Professor Deshmukh shared this incredibly powerful analogy with a student named Sneha. He told her, imagine you are a doctor. A patient comes to you. You don't just check their heartbeat, their ultimate strength, and ignore their blood pressure, their serviceability. This just brilliantly illustrates why we have so many checks. A small crack today becomes a rusted piece of rebar tomorrow, which becomes a total collapse in 20 years. Structural systems are just so highly interconnected, and engineers check absolutely everything to protect the safety of every single person who steps onto their work. The bridges designed today literally carry our children's children. So I'm going to leave you with this final thought and a bit of a challenge directly from the professor's homework assignment. If a structure fails these limits, like our dangerously small beam did earlier, how would you actively solve it in the real world? Would you increase the depth, increase the pre-stress, or maybe increase the concrete grade to fix it economically? Consider how you'd balance safety, comfort, and cost without losing the true soul of engineering. Thanks for joining me for this explainer, and keep that curiosity fired up.